Hello, and welcome to Physics Paper 2, Edexcel 2018 series. Okay, so we're going to go through this paper today. Remember, like as from the other video, which you probably watched, if you're watching this one, paper 1, is that you have to read all the instructions on the paper. Okay, so remember, okay, in a real exam, write in blue and black ink, give you a summary this time because I detailed the other paper. And always write in blue or black ink. I'd recommend black because they photocopy the exam paper when you do it. Okay, and read all the questions. Never leave a question unanswered. Okay, so I'm just going to highlight one thing. When the paper tells you to go and look for an equation, at the back of the paper, see I've gone to the back, page 34, 36, there's an equation sheet. Okay, so lots of the time the questions will say, look for the specific equation on the equation sheet. It might not, it's very unusual. If you really can't, if you really are stuck, have a look at the equation sheet. We'll see how we go with this. And usually also like they tell you, but just in case, remember that equation sheet is at the back there. Okay, it is for you to use. So you don't have to remember those equations, but you have to remember how they are used. Okay, so let's look. Number 1, let's have a look at the first question. So, figure 1 shows air inside a cylinder with a movable piston. Okay, so it means that it can move in and out. Okay, movable piston. So it's like a bike pump. That's what you think about that. Okay, so air, cylinder, piston. So it moves in and out. That is to show it can move in and out. So it's like a bike pump. The piston is pulled a little way in the direction of the arrow, that way, but stays inside the cylinder. Okay, it doesn't come out. Which of these increases? The mass of the air inside the cylinder, or the rate at which air particles collide within the walls of the cylinder, the volume of air inside the cylinder, or the pressure? If we're moving it outwards, the only thing that's increasing is the volume because the area inside is getting bigger. So what we do, we put my pen on, okay, all we're doing is increasing the volume. Okay, so you put a cross in the box and make it clear what your selection is. So you have a pencil, it'll be a lot bit easier for you than here, but you have to make sure which the answer. If you make a mistake, make sure you cross it through and write clearly in the next box. Okay, figure 2 shows a rubber tube that can be used inside a bicycle tire. The tube, so it's before inflating, after being inflated. Okay, let's have a look. The air inside the tube exerts an outward force on the wall of the tube. State the angle that this outward force makes with the wall of the tube. That sounds a lot harder than it is. It's only 1 mark. If it's making, so if you've got a tire and it's making an outward force, the only way it can do that is a 90-degree angle at right angles. Okay, so at right angles with the wall of the tube. Okay, so at, oh, that's a big A. So at right angles. At right angles. Okay, if we think about it, I'm going to draw it. So if you think about, it's going to draw a little section of the wall of the tube, that the particles are all doing that. They're pushing out. And that is at right angles to that surface. Okay? Let's look at the next one. It's only 1 mark. So even if you don't get that correct, it's only 1 mark. You really don't understand. And exam, if you get stuck on a 1 mark question in exam, move on to the next one. It's only 1 mark, come back to it. Okay, it takes 4.8 liters of air from the atmosphere to inflate the empty tube to a pressure of 400,000 pascals. Atmospheric pressure is 100,000 pascals. Calculate the volume of the air inside the tube. Assume the temperature of the air inside the tube is the same as the temperature outside the tube, so we're not going to involve temperature in this. Use an equation selected from the list of equations at the end of this paper. Okay, so straight away we've got one asking that. So pressure and volume. So litre is actually volume. Okay, so let's have a look. To calculate pressure or volume for gases of fixed mass at constant temperature, so we're going to need this one, P1 V1 equals P2 V2. Let's go back. I think probably on about page 4. Oh, not quite. We're on here, near about. Okay, let's write down the equation. I would recommend writing down the equation first. So P1 times, when you get letters together, it means they're times, equals P2 times V2. Okay, so this bit here, P1 times V1, is the pressure before and the volume before you've inflated something, okay? And this is the pressure after and the volume after. Okay, so but this different look at the order though. So it takes 4.8 litres of air from the atmosphere to inflate an empty tube to a pressure of 400,000 pascals. So we know that outside, so this was a measurement outside. Let's just write this down one thing at a time. Okay, so let's have a look. So P2, so pressure 2. So all we have to do is match the volumes and the pressures up. So outside the air outside the tube was 4.8 litres. Okay, and the pressure when it was in the atmosphere was 100,000. Okay, 100 and then 3 more. 1, 2, 3. Okay, pressure 1. Okay, we know inside the tube is 400,000, but we don't know its volume inside. This is actually quite a tricky one, but as long as you match them up, it's actually just ratios. Okay, it's just ratios. So now we have to rearrange it. You can actually, I taught this in class once, and students were like, you can actually kind of work it out a little bit in the head. After a while, you will get to, you don't do it. It's a ratio. If you do enough of these equations, these pressures and volumes, it's all just ratios. Okay, oops, times 4.8 divided by, just rearrange, 400,000. Okay, that gives us an answer. It's actually got a nice calculation of 1.2 litres. Okay, that litres didn't matter actually, as long as the numbers are the same, it doesn't actually matter the units, it's a ratio. Okay, so the more you see of these, the more you'll get used to it. It's a ratio of pressure and volume. So as pressure goes up, volume goes down, and the other way around too. So you get used to these. So if you don't quite understand what's going on, okay, have a look at doing some practice questions with that. Okay, pressure and volume. It's not as hard as that looks. Okay, your students start to see after a while what's going to happen there. Okay, note number 2. When a bicycle pump is used to inflate the tube, the air in the bicycle pump gets warm. You should ignore any effects of friction in the pump. So it's not the pump itself, that mechanics bit, it's to do with the gas. Explain why the air in the bicycle pump gets warm. Okay, so when a gas is compressed, work is done on it. When a gas is compressed, okay, work is done on the gas. Okay, work is done on the gas. Remember, work is force times distance. If you're compressing a piston, it's force times distance. That's work. Okay, so this, I'm actually confused since I put in a comma. This increases the kinetic energy, okay, of the air or the gas. It can be any gas, it's air, but it can be any gas. Of the gas, increasing the thermal energy. Okay, cool. So that's the end. So yeah, so is that work being done? Let's just get my so remember, work done is force times distance. If you're moving a piston, you're putting a force times the distance, you're doing work on something, okay, on the gas. Okay, let's move on to the next one. 2A. A student uses the apparatus of figure 3 to determine the heat capacity of water. This is quite a common question, this one. So we've got a joule meter. All that does is measure the energy supplied. It's really a power supply that actually tells you how many joules straight away. Okay, because you can actually calculate joules. You might have done it with a voltmeter and ammeter, but this device, if you've got one of these, you've got lucky. It measures directly the power, the energy supplied, and you can work at the power by time, but you need a timer or something. Okay, so you've got an immersion heater. An immersion heater is just a heater that goes in water. It's a bit like one of the ones, if you have a tropical fish in a fish tank, it's like one of those heaters that's in a fish tank. And a thermometer, that's just to measure temperature, obviously. Water and a polystyrene cup. So it's not one of those ones if you buy sort of tea or coffee from like an outside sort of stand or something, or from like a sort of a cafe, sometimes you get something in a polystyrene cup, you take it away. Okay, state the measurements needed to calculate the specific heat capacity of water. Okay, so this is yeah, it's quite a common question. Right, so let's look. What I would do is remember the equation for heat capacity. Okay, so specific heat capacity, and work from there. Okay, so you may remember it as E equals MC delta. Oh, that's supposed to be a delta and A. Delta is a triangle. Let me just cross it out. Sorry, delta. That's a delta, not a T. Yeah, that's a delta and A. So E is energy. M is mass. C is the heat capacity. Delta T is a change in temperature. Delta means a change in. Okay, so let's think about from that. If you know that, you can actually think energy will be by the joule meter. So we know the mass of the water. So measurements. So state the measurements. So the mass. So it's not an extended answer question, so don't worry about writing statements for this one. You have a star next to it if it's extended writing. So mass of the water. This is more statementy. Okay, that's one of them. We need to delta T, measurement of the temperature rise, so measurement of temperature change. Okay, measurement of the energy supply. That's what we're using the joule meter for. Of the energy supplied. So we need a little bit more detail to add this to get the additional mark. Mass of the water with balance. Temperature rise, so temperature before and after. And after. Okay, so that is all the measurements that we would need to make. Okay. So state 2 ways in which the apparatus could be adapted to improve the procedure. Okay, so this is actually really nice question to get. Okay, so if we look at the polystyrene cup, we're measuring the energy input into it. Think about everyone hasn't got a lid, all the energy is going into the surroundings. So we could just add a lid or insulation. Okay, so there's lots of easy marks to gain here. So add a lid or insulation. Okay, you could also stir the water to make it heat evenly, and that will give you 2 marks. Actually, really nice and easy, that one. Okay, now graph. Who's going to graph with this? Okay, the student decides to measure the temperature of the water every minute while it is being heated. Figure 4 shows a graph of the student's results. Nice straight line there, isn't it? Predict the temperature of the water if the heating continues up to 8 minutes. So it's up to 8 minutes. So actually what you need to do there is get a ruler and draw a line through the points. So it's a pretty straight line. Okay, so you need to get a ruler and draw a line through the points. And we've got a tool and draw a line. We've got one here to draw a line, so we'll do our best. So let's draw a line. Oh, not pressing hard enough. Oh, I know, sorry, I'm just chosen the wrong thing. Okay. So you need to continue it up to 8 minutes. Okay, now we go across to 8. Okay, you read, I think my line's a little bit, let me just rub that out, it's a little bit too steep. Okay, let me just sort of try it again. So yes, you have to make sure your line's not too steep. So always can go from one to the other like that. And then keep going. Okay, 8 minutes. Okay, so we've got about 105. Okay. Celsius. Okay, so always make sure that that line is a bit straighter than I've drawn it. Okay, with a ruler, so because it can affect, it can affect the temperature. It can affect the temperature you get there. Okay, so let's just what's the next question? So another student decides to melt some ice. The student melts 380 degrees of ice at 0 degrees. The specific latent heat of fusion of ice is 3.34 times 10 to the 5 joules per kilogram. Calculate the thermal energy needed to melt the ice. Select an equation from the list of equations at the end of this paper. Okay, so we've got melting. So this is straight away the latent heat of fusion. Thermal energy for a change of state. So change of state would be latent heat of the mass. So Q equals ml. Okay, so another student decides to melt something. Let's write this down. Oh, turn my pen off again, didn't I? Sorry. Q equals M times L. Okay, that's the energy. That's the mass. And that's the latent heat. Okay, so you don't even need to rearrange for this one. You're getting 2 marks. Q equals mass. So 380 grams. Okay, so I want to be careful. We need to put in kilograms. If that's in kilograms. So it's 0.38 times 3.34 times 10 to the power 5. Okay, so you have to rearrange. We have to be careful. Okay, you have to be careful of conversions in that one. So the answer is 1.27 times 10 to the 5. Okay, so 1.27. Not much room to write this, is there? 10 to the 5 joules. Okay, so I'll finish part 1 for there, and I'll see you in part 2.